Well, Physics 30, so we're back at it. So here's a worksheet for that isotope and mass defect practice sheet. They don't seem too bad. You're just converting between joules and electron volts, calculating mass energy equivalents here. First question just says, how many protons and neutrons do each of the following nuclei contain? So strontium 90. So 90 is just telling us how many nucleons it has, not how many neutrons, but how many nucleons. First, I've got to find out what strontium is. Strontium 90. So let's go in the 90 range here. There's strontium. 38 SR. So strontium is 38, and this is strontium 90. The more typical one would be like 88 or something like that, around that number. So this is telling us that we have 38 protons. And I'm going to subtract the two numbers there, because that top number is the nucleons, which is both protons and neutrons. So I'm going to subtract 38 and get 52 neutrons. Okay. Carbon is 6. That one I just know. So that means I have 6 protons. And in this case, it's not carbon 12. Carbon 12 is the more common one, but this is carbon 13. So I have 7 neutrons. I'm not using my calculator right now. Iron, it just tells us what it is. Iron is 26. So I have 26 protons. And I have 30, because I had to add up to 56 neutrons. Okay, and 6, or D here, I have 1 proton, because that's what hydrogen is, and I have 0 neutrons, because it's just a hydrogen 1. There's 1 nucleon, and that 1 nucleon is a proton. Can I convert this energy into electron volts? I sure can. I can take this number, I can divide it by 1.6 times 10 to the negative 19 joules per electron volt. I'm going to get a pretty big number here. That's fine. 1.6, 10 to the negative 10 divided by 1.6, 10 to the negative 19. Okay, so I get 1. How many zeros do I have here? I'm just going to start from this side. 0, 0, 0. 0, 0, 0. 0, 0, 0. Okay. There's a bunch of zeros. So this is how many electron volts it is, but I'm going to change my prefix. So kilo, mega, giga. So this is 1.0 giga electron volts. Very cool. What's the energy equivalent of 0.25 atomic mass units? So to do this one, remember I had to go use MC squared, but the mass has to be in kilograms for this to work. So I'm going to times that atomic mass unit number by 1.66 times 10 to the negative 27 kilograms per atomic mass unit. Okay, so it's just a quarter of that number. Doesn't seem like that much, but in terms of atomic physics, it's quite a bit. Okay, so this ends up being 4.145, times 10 to the negative 28 kilograms. Then I'm going to put that into this formula. I'm not going to bother, like I said before in one of my lessons, bother writing that out. I'm just going to times it by the speed of light squared. So I'm going to get 3.735 times 10 to the negative 11 joules. That's fine. It doesn't specify what it is, but I like to represent them as electron volts. So I'm going to divide by, just like the previous question, divide by that 1.6 times 10 to the negative 19 number. So I get 233,437,500, which just turns into 233 mega electron volts. How much mass is converted into energy by a nuclear reaction that produces 5 gigajoules of energy here? So let's see, okay. How much mass? It's in joules already, so that's nice. So I'm just going to rearrange this. Yeah. Is that going to disappear on me? Hopefully it doesn't. Okay. Oh, it does. So 5 times 10 to the 6, which is 10 to the 9. That's what a giga is, 10 to the 9. Yeah, that's what we had up there before, too. Okay. Times 10 to the 9. I'm going to divide by the speed of light squared. Probably not going to be that big of a number, which is very convenient because this is like a nuclear reaction. You don't want to have that much mass. You want to be pretty efficient here. So I get 5. Yeah. 5.56 times 10 to the negative 8 kilograms. Doesn't seem very like a lot, right? But compared to the one above it, that's quite a bit of mass. Okay. Determine the binding energy for neon 22. And they give us the atomic mass of neon over here. Now, remember to figure this one out, this is the mass of the nucleus all together, like all one piece here, all 22 pieces. To find how much energy is binding this together, I need to find the mass of all the pieces separated. Now I can do this pretty precisely because I do have that other sheet. Did I leave it open? I don't know. Nope, didn't leave that one open. Get rid of that. Don't need that. I didn't leave it open. I can find it. Where is it? It's under this sheet here, number 2. Okay. I'll share this sheet with you as well, apart from putting it on the assignment. But I do have these 2 masses down here of the mass of a proton and the mass of a neutron in atomic mass units. So I'm going to use those 2 numbers. Okay, so neon, let's find out what neon is first of all. Neon is atomic mass, atomic number 10. So neon is 10, 22. So we have 10 protons. And we have 12 neutrons. Okay, so the mass on this side, if we think of all the different pieces, would be 10 protons, which is 10 times 1.007276 atomic mass units, plus the 12, 1.008665 atomic mass units. So I'm going to add those together. Let's add these together. We get 674 atomic mass units. Okay, so that is more, like the pieces, all its pieces have more mass than when they're together. So if lost mass when they come together, okay? So there's a mass defect. And the mass defect, I'm just going to subtract the 2 numbers. I have the number in my calculator, so I'll just use that. 21.991385. So there's a change in mass of 0.185355 atomic mass units. Now to find the binding energy, I got to use this formula, but I need my mass in kilograms. So I'm going to change this. I'm going to times this by 10 to the negative 27, 1.66, sorry, kilograms per atomic mass units there. So I got the number in my calculator still, so I'll just do that, times 1.66, e to the negative 27. Remember that number is just found in your formula sheet. And I get a mass. I'm running out of space here, so I'm going to take that mass, whatever I find there, and put that, remember this is my defect, and put that into my binding energy formula, which is just Einstein's, part of Einstein's formula there. So I get a binding energy. I'll kind of just jam this in here. 2.77 times 10 to the negative 11 joules. And if you were to convert that into electron volts, 173 mega electron volts. It's a much nicer number. I like that. Okay. Potassium isotope of potassium has this. Okay, what's the mass defect? What's the binding energy per nucleon? Okay, I like this number, per nucleon. Because usually that's talking about stability. How stable is this atom? Okay, this very particular isotope, sorry. So eventually we're going to divide by 40. The goal of this is to find the binding energy and then divide by 40. Up here, just determine the binding energy. So question 1, what's the mass defect? So potassium 40 is 40, potassium's 19. So we have 19 protons. We have 20, no, how many, what do we have here? 30, no, not 31. That was before, right? Wasn't I right? 21 neutrons. Okay, so I'm just going to find the mass beforehand. So I got 19 of these numbers up here. I can just use the numbers that I have up there. That's my proton number, right? Yep. Plus 21 my neutrons, 1.008665. Add those together and get my answer. Plus 21. 8, 6, 5. So I get 40.320290 atomic mass units, which is more than that together. So my mass defect here, if this is for question A still. Okay, so we're still for question A. I'm going to take these two numbers and subtract them. 40.320209 atomic mass units minus 39.963998 atomic mass units. I'm going to just take my number, 39 point, what is it? 963. Oh, my calculator's dying. It's actually just my phone, but I'm still dying. Okay. Let's just increase that up for a bit. What do we get? 0.356211 atomic mass units. I'm going to change that into kilograms. Remember, to do that, you times by 1.66 e to the negative 27. So I get 5.913 times 10 to the negative 28 kilograms. I'm just going to show that working there. Okay, that's good. Now for question B, we are going to find the energy released by this change here. I'm not going to bother showing that. I'm just going to punch in my calculator. And we're going to get joules here. So 5.3217 times 10 to the negative 11 joules. Okay. Again, I'm going to change that into electron volts here. So I'm just going to divide by my number. 333 mega electron volts. Negative 19. That means that's joules per electron volt. Okay. Okay, and the last step is I'm going to take this. I want the energy per nucleon is that number divided by how many nucleons are there? There's 40 of them. So I'm going to divide it by 40 nucleons. 40. So I get 8.32 mega electron volts per nucleon. There we go. Very cool. Yeah, those are pretty fun questions. And I'll see you in the next video. Bye.